So here's another one of those to look at. It's the integral from 0 to 1 of 1 over x squared. So that's pretty clearly improper because we know 1 over x squared is going to be undefined when x equals 0, which is one of our limits. Or, we could do -1 to 1, and as long as the undefined point is in the interval that we're trying to integrate, we know we have an improper integral. So from 0 to 1, all right, that's looking like this. So what do you think, finite or infinite? So now we've got the idea that some of them are finite, some of them are infinite. So the way to find out is we turn the integral into a limit. We say this is equal to the limit as a approaches 0 from the right, because our, basically we want to think of a as being a number greater than 0, and we're going to do the integral from a to 1, and then we're going to let the a get closer and closer to 0 and see what happens. That's what we mean. The limit is a approaches 0 from the right of the integral from a to 1 of, let's go ahead and write that as x to the -2 dx, so we can do the antiderivative, but that antiderivative is easy enough to get. It's going to be, so this is equal to, well, I'll keep the limit as I do the antiderivative, -1 over x from a to 1. So that equals the limit as a approaches 0 from the right of, and we go ahead and plug in our limits. So we're going to have -1. It's going to be minus -1 over a, so we'll make it plus 1 over a from a to 1. And then, so the limit doesn't really affect the -1, right? I could split this up as the limit as a approaches 0 from the right of -1, but limit as a approaches 0 from the right of -1 is just -1. So that's -1 plus the limit as a approaches 0 from the right of 1 over a. So over here we got limits that we need to think about in various ways. So one of the clearest ways to think about a limit like this, well, we can think of it a couple ways. We can think about it graphically. So here's a graph of 1 over a. So if this is a, this is the graph of 1 over a. As a approaches 0 from the right, clearly the limit approaches infinity. All right. We can also say that we are looking at a fraction, a rational expression, where the numerator is bounded and the denominator increases without bound. And that's sort of a very fundamental idea that if I have a fraction where the numerator is, I say bounded, in this case it's just 1. But for example, if the numerator is sine of x, then we know that that can't get larger than 1. So that numerator would be bounded. Bounded. There's something that this numerator can't get more than 1. Well, this limit is stuck at 1. All right. But the denominator increases without bound. That means actually, I'm sorry, the denominator is approaching 0. Oh boy, did I ever mess that one up. The denominator is approaching 0. Approaching 0, not increasing. Silly man. Approaching 0. So if the numerator is bounded and the denominator is approaching 0, then that limit is always going to be infinity. And you can look at a consideration, is it going to be positive infinity or negative infinity? Since we're approaching 0 from the right, all the a's are positive, and so we're approaching positive infinity. Remember that the rest of the graph of 1 over a looks like that. So if we were approaching 0 from the left, the limit would be negative infinity. So from the graph, from the fact that the numerator is bounded and the denominator is approaching 0, but is positive, we get that what we have here is -1 plus infinity. Now, if I have infinity and I subtract 1 from it, I just get infinity. So yeah, if you think about it, if I have infinitely many things and I subtract 1 of them, I get infinity. There's a song about that, which I might attach as an extra video, a song about infinity minus 1 is equal to infinity. All right, but here's our integral. All right, so that integral was infinite. It's infinity. All right, so here's a fun thing we can do. Let's shake this up a little bit. Let's think about this integral. Here's something else we can do. So, because the idea here is that we can sometimes find the area of a region that has an infinite boundary. Well, what if the infinite boundary doesn't go this way? What if the infinite boundary goes that way? So here's an example of that. We can say, and this turns out to be especially useful for statistics, by the way, and some other things like black body radiation and other neat things. The integral from 0 to infinity, right? So I already blew your mind, right? The integral from 0 to infinity. Of what? of e to the negative x dx. So this is going to have to be something that decreases if we want to do the integral to infinity. All right, what does e to the negative x look like? E to the negative x passes through the point 0, 1, and then has a horizontal asymptote that it approaches rather assertively. So here's y equals e to the negative x. And so this time, the area that I'm finding is all of this under here, going out forever, forever. All right. Is that area finite or infinite? I wonder. Well, now that we got the idea that if I want to do an improper integral, I set it up as a limit where one of the limits of integration is the limit that I take. This time, it's the b limit that is problematic. So I'm going to say, what is the limit as b approaches infinity of the integral from 0 to b of e to the negative x dx? And so once you've seen a couple of these, you get the idea. You just take the limit of whatever is the problematic part of the integral. So this is going to be limit as b approaches infinity. We can go ahead and do the antiderivative, negative e to the negative x. And that's going from 0 to b. So then that's going to be the limit as b approaches infinity of, plug in the b, negative. So you do everything just the normal way. This is going to be minus negative e to the 0. So let's just put plus e to the 0. All right, so that is, now essentially we distribute the limit over the summation sign. That's actually a theorem about limits. Limit as b approaches 0 of negative e to the negative b. I'm sorry, it's b is approaching infinity. And then this one is just 1. And since this variable, this expression is constant with respect to the variable b, we can just say that that limit is just going to be 1. E to the 0 is 1, no matter what the b is. All right, so the next thing is get a handle on what that is. What is the limit as b approaches infinity of negative e to the negative b? Well, if I write this as a fraction, it's a little easier to understand what's going on. Limit as b approaches infinity of negative 1 over e to the b. So essentially the 1 is bounded again, it's staying steady, but then this time the numerator is really doing what I said it was doing last time, which is increasing without bound. So my numerator is bounded, my denominator is increasing without bound, increases without bound. That means any number you can think of, this number is going to get larger than that, e to the b, and the b is increasing. It's because e to the b is an increasing function. All right, so that limit is always going to be 0. So, yeah, you can think about that graphically. Negative e to the negative b, I guess, looks like this. Approaches, so as b approaches infinity, negative 1 over e to the b is approaching 0. You can think of it graphically like that. Lots of ways you can think of it. You can just think as this e to the b becomes a really huge number, 1 divided by a huge number is going to be approaching 0. So this equals 0 plus 1, and you get the remarkable fact that the area under this curve is not just finite, it's 1. It's 1. Okay, so we're going to look at some more interesting cases next.